Hello everyone, my name is Praveen Kumar Pokala. I am a research scholar at the Indian Institute of Science. The title of our paper is Accelerated Weighted L1 Minimization for MRI Reconstruction Under Tight Frames. My co-author is Professor Chandrasekhar Silamantula, also from the Indian Institute of Science. In this talk, we propose a complex domain weighted L1 regularization based analysis parse model and devise the proximal operator based on Wittinger calculus. We also develop an algorithm that solves the MRI reconstruction problem based on the analysis parse model by using Wittinger gradients and majorization and minimization strategy. We also compare the proposed technique with the state-of-the-art techniques under various sampling strategies in terms of objective metrics, namely peak signal to noise ratio and structural similarity index metric. The outline of my presentation is as follows. We begin with the motivation and a brief introduction to the analysis and synthesis parse models. We then review the recent related literature and highlight their limitations. We highlight our contributions that overcome the limitations of the existing work. Then we proceed with the introduction of our formulation for the analysis parse model in complex domain and then present the algorithm for solving it. Finally, we demonstrate the efficacy of the proposed approach in comparison with the state-of-the-art techniques. We seek a faster and better MR reconstruction technique based on complex domain analysis parse framework. We consider the analysis parse model as it is known to be better than the synthesis parse model in terms of reconstruction quality when the sparsifying basis is not orthonormal. Further, a complex domain formulation has not been considered in the MR image reconstruction literature. The actual sparse coding formulation employs the L0 norm in the transform domain, but the optimization is NP-hard. Typically, one resorts to either convex or non-convex relaxation approaches so that the sparse coding problem could be solved in a computationally tractable way. The synthesis sparse model based on L1 minimization approach for sparse coding is a convex relaxation of the L0 problem and results in a sparse solution under certain conditions. Since the L1 norm is convex, global convergence is guaranteed. However, L1 is also known to result in biased estimates of the amplitudes, as pointed out by several authors, notably Selesnik. The analysis parse model results in better estimates than that of synthesis counterpart when the sparsifying transform is overcomplete, as pointed out by Allard et al. This slide shows the convex relaxation of the L0 problem shown in the previous slide. However, it solves the problem in the image domain unlike the synthesis framework, which solves the problem in the sparse domain. Beck et al. Developed FISTA to solve the synthesis sparse problem. In the analysis setup, ISTA and FISTA cannot be deployed directly as there is no straightforward closed form proximal update. To address the analysis model under tight frames, EDMM, smoothing FISTA, and projected FISTA have been proposed. The optimization of an objective function defined over a complex domain requires complex differentiability. MRI reconstruction problems. Consider real valued cost functions defined over a complex domain. They are not holomorphic because they do not satisfy the Cauchy-Riemann equations. To overcome this problem, an alternative tool for computing the complex gradient was proposed by Whittinger. It relaxes the strict requirement for complex differentiability and allows for the computation of the complex gradient using simple yet consistent rules and principles. S-Vista replaces the non-differentiability penalty with a parametric function, namely the Morrow envelope, which is smooth and the optimization is carried out using Vista. The parameter of the Morrow envelope affects both convergence and image reconstruction performance of S-Vista. One can employ the alternating direction method of multipliers in the analysis model. ADMM solves the augmented Lagrangian formulation by introducing an auxiliary variable. The Lagrange multiplier affects the convergence speed. ADMM results in a solution that is close to optimal for a large parameter value but has slow convergence. A small parameter value accelerates convergence but gives a solution that is far from optimal. It is not straightforward to tune the parameters of the ADMM algorithm. Further, the memory requirements are higher because of the auxiliary variable has to be stored. Projected fast iterative soft thresholding algorithm overcame the limitations of ADMM and S-Vista. The image recovery accuracy of P-Vista is better than Vista and ADMM in terms of peak signal to noise ratio. However, its image reconstruction quality measured in terms of PSNR is the same as that of S-Vista. We seek a faster and superior quality image reconstruction technique by considering an alternative formulation that gives an unbiased solution. To alleviate the bias, we consider the weighted L1 regularization in the complex domain and advocate the use of Whittinger gradients. We develop projected weighted ISTA and its faster variant, namely projected weighted VISTA, based on the majorization and minimization strategy. The weight updates are inversely proportional to the sparse coefficients in PW VISTA, which results in a superior performance than the state of the art. We demonstrate the efficacy of PW VISTA with application to MRI reconstruction, considering the shift invariant discrete Haar wavelet transform for sparsification. This slide shows the complex domain problem formulation for MRI reconstruction based on the analysis sparse model. Our formulation weighs the coefficients differently by introducing a regularization weight vector in the transform domain, unlike scalar regularization employed in the existing methods, which assigns the same weight to all the coefficients. The regularization vector is treated as an optimization variable in our formulation to alleviate the bias. ISTA and FISTA cannot be deployed directly as there is no straightforward closed form proximal update. Therefore, we reformulate the analysis sparse model into its equivalent synthesis formulation, which is shown here based on P-FISTA. Since the cost is not holomorphic, we employ majorization and minimization based on Whittinger gradients. We follow the three-step optimization procedure, which solves sparse coding step, update followed by projection onto the column space of analysis operator, and finally updating the regularization parameter based on sparse coefficients. It is important to note that even though the result might seem to be a straightforward generalization of the soft thresholding operator to the complex valued case, its derivation, however, is not trivial. The proposed proximal map is summarized in this slide. On this slide, we show the equivalent synthesis formulation corresponding to the analysis formulation. The cast comprises the sum of two functions, which are non-holomorphic. The data fidelity term is assumed to have a Lipschitz continuous gradient. We derive the algorithm called projected weighted FISTA for solving the problem under consideration. The optimization is performed based on three updates: sparse vector update, projection update onto the column space of the analysis operator, regularization parameter update. We employ Nestro momentum to further accelerate the optimization. We consider a real T2 weighted brain image acquired using 3T Siemens Trio TIM MRI scanner with 32 coils using T2 weighted turbo spin echo sequence from a healthy volunteer. The data was provided by Leo et al. The real and imaginary parts are of size 256 cross 256 each. The case space undersampling is simulated using a random mask which covers 30% of case space, and the radial mask with 84 radial lines. The noise considered is IID complex white Gaussian noise with sigma equals to 0.01. The reconstructions are performed on a Samsung PC running Ubuntu 16.04 operating system with Intel Xeon 94 GB RAM, whose CPU having a frequency of 2.60 GHz. For performance comparison, in addition to the standard metrics such as peak signal to noise ratio and structural similarity index metric, we also consider the relative error defined as shown on this slide. The parameters for all the algorithms are set as recommended in Leo et al. To ensure a fair comparison. As shown in figure A, PW FISTA outperforms FISTA, S FISTA, and ADMM P FISTA in terms of relative error and convergence behavior. The parameters tau and epsilon of PW FISTA affect both convergence behavior and image reconstruction accuracy as shown in figure B. We observe that a lower value of tau results in better reconstruction, but it slows down convergence. On the other hand, a larger value of tau results in faster convergence but leads to a lower image reconstruction accuracy. This slide shows the MR image reconstruction under random sampling with 30% case-space data being sampled and their reconstruction error images using various algorithms. This slide also shows that the proposed method significantly outperforms the benchmark techniques in terms of PSNR. This slide shows the MR image reconstruction under radial sampling with 84 radial lines and their reconstruction error images using various algorithms. This slide also shows that the proposed method significantly outperformed the benchmark techniques in terms of PSNR. The reconstruction accuracy of proposed method PW-FISTA in response to the parameters epsilon and tau is presented in the table shown in this slide. PW-FISTA results in a better reconstruction quality for various parameter values. We observe that PW-FISTA outperforms the state-of-the-art by more than 3 dB in case of random sampling and about 1.3 dB for radial sampling. In a deviation from the standard approach in the MRI literature, we proposed a complex domain weighted L1 regularization to solve the CS-MRI reconstruction problem considering type frames. We deployed Whittinger calculus to derive the proximal operator, which led to an efficient and shrinkage thresholding algorithm called PW-ISTA and its faster variant PW-FISTA. We demonstrated how PW-FISTA responds to the choice of the algorithm parameters. We considered both random sampling and with 30% data being sampled and the radial mask with 84 lines. Experimental results demonstrate that PW-FISTA has a superior image recovery performance with both sampling strategies, while being faster and more efficient than the state-of-the-art. Here are some key references. We would like to thank Ministry of Electronics and Information Technology, India, SEB Matrix Scheme, and Robert Bosch Center for Cyber Physical Systems for funding this research. With that, I conclude my presentation. Thank you for your kind attention.